Hello everyone, how is it going? So today we are going to start with a basic machine learning project which would help us in understanding the basic fundamentals of machine learning which we can utilize in our future projects. So just to get the basics strong, so this is nothing but machine learning 101, so understanding the fundamentals. So we will start with one project, and this is nothing but classification of handwritten numbers. So you can see on the image there are a bunch of numbers, and there is a data set which is called as MNIST, which is registered by the National Institute of Standards, and this is like the hello world application of machine learning, like something where anyone who's starting, he would go through this project, you would understand what is happening, and it gives out the fundamentals of how a machine learning project is developed. So just to give a background on this project, I believe this was something back in the 1980s, and Jan LeCun is one of the members of this thing. If you don't know who Jan LeCun is, Google him up. He's a big name in the field of AI and machine learning. So they were the pioneers of this field, and the convolution neural network. Back then, the GPUs and all these hardwares that are available now, which makes computation of all these deep learning models very easy, were not available, but they understood and they devised this convolution neural network model that they used on this particular data set. So it's a very interesting field, and they basically made this for the United States Postal Service. So when people write down handwritten addresses on the envelopes, this model was supposed to read those labels and understand what the text was, what the addresses were on the envelopes, so they could use it for the mailing purpose. So that's where this data set was created, and now this data set is, it's of course open sourced and everyone is using this. And of course, someone who is starting in, they go through this project. In fact, all the other projects, all the other neural networks that we develop in the future, this data set is considered as a touchstone of machine learning, where any model or any deep learning model that you develop, people try to test it on this particular data set to see how it is performing. So with that, I'll go into understanding what the project is and how we are going to set it up. This is going to be probably a lengthy video. I'm trying to go as detailed as possible, especially for someone who is a beginner and who, even if you don't have much of coding background, if you don't know much about machine learning, this would be a very good starting point. And I'm doing this especially for my own understanding, because when you explain it to someone, you will get to understand things better. So I'm doing this so that we come up with different other machine learning projects. But if we don't understand these fundamentals correctly, then it becomes difficult for us to move forward. So let's understand these basics first. That way we can make a strong foundation for ourselves. So I'm going to first start with what the project structure is, how the machine learning model looks like. So every project, every code that we develop, let it be a HTML web page, a Python application, or whatever it could be, there is a project structure. There is a structure in the machine learning projects as well, of how you start, of how you do, how if there is a header, if there is a body, like a letter. You first have the subject, you then have an introduction paragraph, you have body, you have a conclusion. Similarly, machine learning projects have their own structure, which makes it easier in the flow. So what is the structure in this case? So the first step is the loading of the data. So understanding the data. Now, in our case, it is nothing but the MNIST data set which we are trying to train. So the handwritten text that we have, that is the data. So loading the data, collecting the data, that is the most important step in any machine learning project. Loading the data and of course preparing the data. So you have first collected the data set. Now it could be, in our case, it's just a simple handwritten text of images of handwritten text which is already available, but it could be any other project. Imagine you're trying to set up your own object detection and you want to detect some sort of object. Imagine, take a plant and you have to collect all these images of a plant, or it could be a car that you're trying to detect and you want images of your car, different types of cars, and you want to take images from different angles, from different areas, different colors, and you collect that data and then you feed to the network. So that collection of the data is the most important and pristine, and the type of data you collect, the accuracy of the data or the quality of the data is very important. If your data has some errors in it, has some noise in it, if your data is not correct, so for example, you have a data set of cars and by mistake you inserted an image of a, instead of a car, you had a motorcycle inserted in it, or by mistakenly you forgot to put the shutter, or the camera was not clicking properly, the image came out very blurry, or the image, instead of taking the picture of the car, you took something else and you inserted within the data set. So those issues can cause errors in your data. So now you're giving wrong information to the network. You're telling that your data could not just be a car, but it could be a motorcycle also. So then you're confusing the network and it will train incorrectly, and of course your output will go bad. So what you're starting with is very important. So your data should be pristine, should be very qualitative, and people spend the most amount of time in preparing the data set. So that's the biggest step for us. In our case, in this particular project, we already have the data set. It's a well-known data set, and many people work on it, so it's already maintained and it's in a very good shape for us. So we don't have the effort, we don't need to take the effort of cleaning it. But to give you an understanding, the data, importance of data. So the second is, of course, the preparing the data for the training, where we are nothing but removing the noise, removing the unnecessary information. So later on in the projects, we'll see how unnecessary information can cause problems in your projects. So only the information that is important, that should be prepared, and only information that is quality should be used. So that's the second step. The third step is creating the network. So this is the main body of the project. So creating the network. So what is your network? Network is a series of layers. These are neural networks, of course, and I'll explain you how they look like. So you can see this is a set of neural networks. So these are nothing but layers which are set on top of each other, and these networks have some sort of algorithm in behind them where they filter the data that comes through. So imagine this data over here. This is nothing but an image, and this image goes through this network of layers, and these layers filter the image. Imagine like a sieve that we use in our kitchen. So I have an image pulled up here. So imagine a sieve that we use in our kitchen, which filters out. So you put something inside, it could be a flour or whatever you're putting in, and it sieves out, it filters out the content of it. So these layers are nothing but sieve, and these sieves take out these information from the particular image, and they take out all the essential information. So now, and they have their own way of working. So this particular section here, it's not necessary that you understand what is happening inside them, but you need to understand what these layers can be and how these layers are stacked on top of each other. To make it easier, imagine a series of sieves. So here you can see an image of 4 sieves that are kept on top of each other, and each sieve has its own property. Each sieve can filter data accordingly, and at the end you get this fine powder which comes out. So that is what these sieves are designed to do. So you have these different layers that are set on top of each other, and these layers, they go through that data one by one, and they filter out the information. So you can see it's a bunch of networks, it's a bunch of collections, which is it looks from the top, it looks very complicated, but we don't need to understand these connections. All we need to understand is the input layer, how many inputs do we have and how many outputs do we have. So that's the most important thing. And the layers, these are all mostly goes by trial and error, where you define how many layers you want to go in and see what the output is. If the output is bad, then you come back, you reduce a layer, or you may add a few layers, and then you test it out and see how your network performs. So understanding these complications is not so much of necessity at this moment, but for us, we are only concerned about what the input layer is. In our case, it's nothing but the data that you're feeding to the network, and the output is right here. So whatever output you're giving it out to, or whatever output you're expecting the layer to perform. In this case, this particular image is saying that the output could be either 1 or 2, or 0 and 1. So there are only 2 outputs out of 5 inputs. So this is, I mean, it's just an example for us to understand, but that gives you a picture of what it is. Now let's understand going back to the structure. So the fourth step is compiling the network. So what is compiling the network? Now when you have these sieves, when you have this network that takes the data and goes through the network, and it gives you an output, there is something called as a feedback loop. You need a feedback loop. You need to let your network know how your network is performing, because as I said, this is nothing but a black box. So what happens inside or how it happens, we don't know. Even the network doesn't know. But there should be some sort of a feedback loop that takes the output from here, from this end, and it goes back and tells the network that your output performs so badly. You had about 2% success rate or a 3% success rate. So improve whatever you're trying to do. So work on it. So that feedback you need for the network, and that is where the compiling comes in. This step called the fourth step, it's nothing but compiling the network, which is specifying the feedback loop or optimizing function. So if I have this image, and I took this from the book, I believe the name of the book is Deep Learning with Python, a very good starting book for anyone who's interested in these structures. So you can see this is the project structure. Basically, input X is nothing but the data that goes in, and these are the layers. In this case, they have only 2 layers, and this layer goes through predictions and it gives out some predictions. This is the feedback loop, this loss function and the optimizer. This loss function identifies and lets you know how bad your network performed, and using that information, you give it to the optimizer, and the optimizer changes the weights of the network. So what this does is you just take out the information, you let your network know that how bad you're performing, and this optimizer changes the values that are being used in the layer, and then comes back and then re-evaluates the network. And of course the data goes back again, they go back to the data, they again train the data, and then go back and gives it to the loss function. Again, the loss function looks at it and says, okay, right now you're not 2%, you're about at 5%. So you're doing some improvement, but there's still a lot of work need to be done. So you go back, and then it goes back and then again retrains itself. It comes back and then lets the loss function know, oh, okay, right now it looks like you are at 15%. You still have 75% left to go. So you go back and then you tell the optimizer, change again. You make a bunch of changes, and this cycle goes on for quite a bit of times. And at the end, the loss function comes back and tells, okay, I think enough done. We are now at 99% accuracy. I think this is good. This is what the user can work with. So let's go ahead and release the network. And at that point, you've released the network, and then you're good to be using for your predictions. So let's see how this understands. So we come back to the structure. So compiling the network, and then of course training the network and understanding. So let's go back to this Google Colab link. So if you look into the description box below, you can see there is a link which will open up this particular file here. You can go ahead and sign in with your own account, so you can test it by yourself and follow along our steps. So we'll do this whole project is divided into 5 steps, and it's all easy to set up. So let me go ahead and clear all the outputs so I can start fresh with you. So coming down to the first step. Now, as we discussed, the first step is loading the data set. And in our case, it is the MNIST data set. Now, you can see I'm using Keras here. Keras is nothing but a data framework for deep learning modules. You can use any other data frameworks like TensorFlow, Theano, Caffe. There are different others. But Keras is something that sits on top of everyone. So if you use Keras, you'll or even if you're using TensorFlow has a very good community build up behind it. So TensorFlow is what many people are recommending, but Keras and TensorFlow, they go hand in hand. So you would be safe if you open any one of them. So you'll be fine. Now, MNIST happens to be already part of the Keras datasets. Keras datasets has a set of datasets that are already available, and MNIST is fortunately a part of it. If we were doing some other project, our own hobby project, or our own, like I said, if you're trying to detect images of cars, then you would have to create your own data set. But in our case, we're lucky enough, we do have the MNIST data set, which is nothing but this bunch of images of all these handwritten text images, which are already in the data set. And this MNIST data set is divided into 2 types of data. So one is called as the train images, and the other is called as the test images. Now, what is train and what is test? So let me go back to the framework here. So when you give the data, you divide the data into 2 types. One is the training data set and the other is the testing data set. Training data set is what goes here. The training data set is what goes here. And the testing data set is what comes here to the loss function. And these 2 data set, you can see here the target Y and the input text. So these are both separate. They should not be overlapping. The training data set is separate and the testing data set is separate. Training data set could be 80% of your whole data, 80 or even 90% of your whole data, and testing data set could be just 10% of your data set. So if you're talking about 10,000 images, you can have 80,000 to 10,000 images. So you're talking about 8,000 to 9,000 images in your training data set and about 10,000 images in your testing data set. And why do you do that? The reason you do that is because your loss function takes your test images and uses the network that you created over here to test and see how it performs on the test images. Now, you used the training images, of course, to create and then form your network, but the loss function works on its own. The loss function is like your teacher who grades your test. So that you have written the test, and now the loss function comes as a teacher and it tells, okay, I have my own data set. I'm going to test it. I'm going to test your paper with my own data set to see how my answers are going to perform. So it takes your test data set, which is only 10%, and then sees how it performs, how your network performs. If it gets a good accuracy on the test data set, because test data set is something which your network has not seen, and it sees whether it's going to perform good on the test data set. If it performs good. Otherwise, you then go back and then retrain the network. So that is why you divide your training data, your whole data set into 2 parts. One is the training images, and of course the other is the test images. So in case of the MNIST, this is already divided for us. When you just call the load data function here, MNIST load data, it gives us output in 2 formats. One in this case is the train, and the other in this case is the test. And you can see that it's also giving us the labels and the images. The images are nothing but, of course, the images. Labels are defining what that image is. So whether it's an image of a 0 or a 1 or a 2 or a 3 or a 4 going up to 9. So the labels are just nothing but defining what that image is about. So the next step is to understand this data set. So let's run this by clicking on the play button here, so it can load the data set for us. And once it loads the data set, so you can see that it's using the TensorFlow backend. That's because we are using the Google Colab. And once it has downloaded all these images for us, it's ready. So you come back and then let's understand what's the shape of these images, or what's the shape of this data set. So that will give you an understanding of what we are working with. So you can see that it shows 60,000, and 60,000 is nothing but the number of images that are available in the train images. So when you loaded the data, it gave you the train images and the test images. The train images has 60,000 images in it, and the test images has about 10,000 images in it. So instead of train image, if I were to put down test image here, and this before I leave this 28 by 28 is nothing but the size of the image, the pixel or the resolution of the image. So let's call test here. So if I say test and if I run test, you can see that it's now giving 10,000 only. So 10,000 is nothing but the number of images that are available in our test data set. So let me go back and change it to train images so it doesn't messes up your Colab network. And the next step is to understand these images and what these images are. So let me comment this line first and just show you this part. So in fact, let me comment this side as well, so I can just show you what this image is. So let's take train images 1. So train images 1 or nothing, it's we're just printing the first image in the training data set. So if I print this, so it gives out a bunch of arrays, and you can see the values are ranging from 0 to 253. There is also, it goes 0 to 255, and you can see it's a big array, and this array is representing nothing but a number. And let's see what that number is. So if instead of printing this, if we use the Matplotlib, and Matplotlib helps us in displaying the data on the Google Colab. So we are going to be displaying the data, and we're going to say this digit that we had used, the array of 1, the first digit, or it's not the first, it's the second, because you're calling 1 instead of 0. So the second digit that is available, you're just asking Matplotlib to display it for us. So now we'll erase this thing and we'll run, and let's see. So it's coming out to be a 0. So the second image is for some reason a 0, but let's see what happens if you put 0 here. So you'll get a different image. You can see it's a 5, and if I were to put down, say, just a random 6 over here, so it's giving 1 over here. So because all these images are put in random, so instead of 6, let's call 151 or 150. Okay, 150 is a 4, so it happens to be a 4. So we can see what this is. Now I also want to show you test data set. So let me uncomment this. Oh, sorry, let me comment this, but we do need the Matplotlib, and let me show you what the train images are. So this 4 is nothing but part of the train images, right? And now I'm going to show you what the test image looks like. So let's see test images 0. So test images 0. So this is something which I want you to remember. So you can see test images 0 is a 7, because we are going to use this for our prediction later on down the lane. So that way we know what the 7 is. So now let's do another number. Instead of 0, let's think about 150. So, and let's run this. So 150 is a 9 and 0 is a 7. So let me go back and change it to 0, and let's do 0 here. So okay, so the 0th image of test images is nothing but a 7, and we saw 150th images is a 9. So let's go back and let's go down, and the second step is to converting the images. So this project structure defined that you want to prepare the data set, because your images are in the range of 0 to 255, because we saw when we printed that big array, it had an array which had data set of values which were ranging from 0 to 255, and that is a big number for our network to play with. So we convert that number from, instead of 0 to 255, we converted it into a range of 0 to 1. So how you can do that? Simple. Just divide the number by 255, and that will give us the factor. So it's called as normalization, but what you're doing is just restricting your values between 0 and 1. So you do that by doing this. Your function over here, you're defining the train images, and you're just telling divide by 255 right here. So initially it's an integer format, because 0 to 255 is an integer. It's an unsigned integer. You're telling it to convert into a float, because it's going to have decimals in it. So the decimals are going to take care of all the division. So you're dividing it by 255, and that, once you do the 255, it will convert the whole image into nothing but 0 to 1. So let's run that, and now we have normalized the images, both the training images and the test images, so it's easier for our network to perform. Now the next step, which is the third step, now this is the body of the image. Until now we created the data set, we prepared the data set, and we are ready with the data set. Now we want to create our body, which is the network, the most important aspect. And here you're using the Keras two important functions. One is the models and the other is the layers. So models is nothing but your network, that network which you're going to define, and layers are the each single bit. So if I go back to this image over here, this whole section, this whole body over here is called as a model, and this each box here, each box which represents a layer, is called as a layer. So going back to the function, so step 3. So you can see how we are taking the models and the layers, and you're defining the models to be a sequential. So let me maximize this a little bit so it's easier for you to read. So you can see, you can tell that you're telling models sequential. So what does that mean? It means that you're telling your function, your model, that your layer is going to be a sequential layer. What does that mean? So if I open the sieving back, this is a sequential layer. So you have the big coarse sieve here, you have a little finer sieve, then a little more finer, and then the most finest at the last. So it's a sequential process. You put this material on the first sieve, and it goes through all the sieves one by one. So it's a sequential process. That is what you're telling your network. You're telling your network that it's a sequential network, and you're going to have some layers in the future that you're going to see, and all those layers are supposed to be run in a sequential format. So that is what you're defining, and this is your layers basically. So you're defining two different types of layers here. One is a ReLU activation, and the other is a softmax. Now I don't want to complicate this thing by going into what these activation functions are. This will be a different video altogether, and I'll go back and refer to this video here, so you understand what ReLU and softmax is. But these are nothing but activation functions that specify, these are just like gradient functions that take the data and then understand what the data is depending on the value present in it. So you're defining the input shape also. Let me minimize this a little bit. So you're defining the input shape, and the input shape is nothing but a 28 by 28 image for us, which we know coming from here. If we go back to the image data set, we know that the image shape is 28 by 28. So you're just letting your function know that the first layer over here, which is the activation ReLU function, the first image, and this is the layer that interacts with the images. So you're letting the images know that it's going to be a 28 by 28 image, and you're just taking that data set from there, and you're coming down and you're specifying the second layer, which is a layer of softmax, and this has 10 functions, 10 inputs in it. This one had 512 inputs, and that is because of the images that we are using. And the number of images, the number of or types of information that you're going to be extracting is going to be defined by this one. So that is that, and the next is the second layer, and you're telling the second layer has only 10 input layers, and this is because you're going to be having 10 numbers 0 to 9. So you're letting your function, your layer, know that you're going to have 10 different types of outputs. So this is a softmax function. Again, understanding softmax and ReLU is going to be a different topic on this channel, so stick around if you are interested in understanding what those are. But for us, as going into a beginning level project, let's not go into deep of that. But for now, for our understanding, let's just take it as though that these are nothing but those monitors that are going to be using in order to run the function. So all these computations, the mathematics which is going to happen because of these softmax and ReLU functions. So once you have defined your function, if you press the play button, once you have defined the function, then you compile the network. And compiling is nothing but defining your loss function and your optimizing function. So if you go back to the architecture, this loss function and this optimizer function is what the compiling is going to do for us. So the fourth step is the compiling process, where you're telling the function that your optimizer is an RMS prop and your loss is a categorical cross entropy loss. And of course you're telling the metrics to be accuracy. So what it does is you're just defining what your optimizer function is going to be, and you're also defining what your loss function is going to be. So again, I'm sorry to keep it short, but if I go into the details of these two functions, optimizer and loss, it'll be too complicated for this beginner video. But for us just to understand what the machine learning basics are, I don't want to go into it right now, but we will be going it into the future projects. But to understand, these are nothing but mathematical functions that sit behind the network and do these computations for us. The optimizer function has the responsibility of changing the weights of the network so that the network can go back and re-evaluate itself on the training images. The categorical cross entropy is nothing but it's going to take your test images and see how your network is going to perform on those test images and let us know what the accuracy is going to be. And the accuracy, the metric, you're letting the network know that accuracy is what we are concerned about, and based on the accuracy we're going to know whether or not our function is performing nicely or not. So that is what the metrics is. Metrics is nothing but letting the network know what we are more interested in. So let's play this button here. So it has created and it is now ready for our network. The next step is converting into a categorical format. So what we are doing here is this numbers that we have, these are in the range of 0 to 9, and we need some sort of depiction of how this function is going to be. So this layer that we have here is 10 outputs. So this layer that we defined, the last layer, it's going to give us 10 outputs. Now what these 10 outputs could be? So these outputs are nothing but letting us know what your numbers are. So it's going to be from 0 to 9, correct? So that's the reason. If you consider 0, then you have about 10 digits that are going to come out. And you are going to say that each digit is going to be in this format. So it's going to be 0, 0, 0, 0, zeros, and only where the digit is supposed to be present. So for example, if you're representing a 5, so the 0th number or the number which has the fifth digit, the fifth position in that row is represented by 5. So if you count from here 0, 1, 2, 3, 4, 5. So wherever 5 was present, if it's a 5, then a 1 should be present in the fifth position of that array. So that is what you're defining. So a 5 is represented by this, and if we had if we were to put down 0, or if you were to put down, let's take an example of 0. If we were to put down 0 in the place of the first digit, instead of a 0 here, you could put down a 1. And if you were representing a 9, the last digit over here, everything else would be 0, and the last digit would be a 1. So that's how you find out what your network is predicting, because your network is trained on zeros and ones. And for us, in order to understand what the output is coming out from the network, you needed something where it's readable, it's understandable by the network as well. So that's the reason we are converting our output from 0 to 9 format. Instead of that, we're converting into a binary format of zeros and ones right here. So we do that by using this function called toCategorical, and you're defining that all your training and test images are going to be converted in this format, because that's how your neural network is going to give an output for us. So that's the reason we are converting all our training and testing images in that format as well. So if you play the play button here, it will convert it into this categorical format, and everything is done. So this was the last step of preparing the data set. And once this is done, we are ready to train the function. And this is the fun part in any machine learning project, where you have all the all the 4 steps that we did in the beginning. All this thing that we did was for this step, and this is the end step, and this is where the network is training, and it's going to give us the output. So all that hard work that we did up there is for this particular step here, and this is called as a fit function. And this fit function is going to help us in training, and it's training your network. So you're telling the network to start training on the train images, and of course use the train labels so you know what these training images are. And you're giving an epoch of 5. Epoch of 5 means that you're going to run this network 5 times. So that feedback loop, which we talk about here in this image, this feedback loop is going to run for 5 times. That is what the epoch is about. And the batch size is 128, which means that it's going to take 128 images at a time to read through. And this batch size should be set appropriately. It should be set in a way that it's collecting all the images, all the different types of images in one go. And it's important that you're randomizing your data set. Otherwise, what happens is if you have your images in a sequential format, then you run into problems where your data set will not be training properly. So you need to randomize your data set. That's why when you saw the MNIST data set up there, you were right here when we were trying to display these images. We had images randomly placed. We put down some other arrays here, and it was giving some other value. So it was randomly placed, and it is very important that we randomize the data. Otherwise, your network is going to read in a sequential format of these images, and it'll go all wrong. It will be a messed up thing because of this batch size. Because this batch size, you're not reading your training images all together. You're reading them one by one. And that's the reason you want to randomize your data, so it's a collection of everything in there. And once we specified your training, if you go ahead and play, you can see that it starts training. So it's training on all the 60,000 images one by one at batch sizes of 128, and it's going to go until, so it's 1, 2, 3 is going on right now. The third image is going on. So you can see, and it'll go till 5. And you can see the accuracy. It started off with 92% here, 96, 97, 98, 98, and we are done with 98%. So that's the beauty of it. We started off with 92%. The loss function kicked in. It told the network to go back and change your weights. It changed a little bit. You got 96%, then you got 97%, 98%, 98.8%. So that's how the accuracy is changed, and we can see how we performed. So this is evaluating the function, and this is using the test images. Now, so this is where you can have a overall outlook, and you can see how your network is going to perform. So if I press the play button here, it's going to tell us that it's having a 97.9%. So you can see that on the training images it had a success rate of about 98%, and on the test images it is only 97%. So that's how your network is being evaluated, and you're telling the network that okay, this is at 97%. And the reason that happens is because of overfitting, and we'll go into overfitting later on in the next videos, but this is just to understand how the network performed on the test images. So once we have the network is ready, and it's saved in this particular variable network, and it's all ready, you can use it to predict the network to see how the function is performed. So we knew that in the beginning that when we tested here, right here, that the 0th image of the test images is a 7, and let's see what the output would be. So if I come back to the last step, which is the prediction step, and here you're telling the network to predict, and you're telling the network to predict on the test images, and tell me the prediction of the 0th image right here. So if I press play here, let me delete this one over here, and if I press play, it will give us an output, and it will give us an output of 7, and it's saying that the test image that you gave, it's a 7. So we also looked into 150. Let's look into 150, and if I press the play button, it gave us a 9. And if you remember, go back to the video, it was a 9 that we had when we had seen, and it's giving us a prediction of 9 right here. So that means that our predictions are performing nicely, and it's giving us the right output. So that's about it with the MNIST data set. This is nothing but the machine learning 101 to give us an understanding of what machine learning is and how machine learning runs. So I think this would be a good starting point for someone who is getting in. And with that, I'll come to the conclusion of this video. If it's something that you're interested in, if it's something that is helping you, and if you're interested in this machine learning topic, in this channel we cover topics about machine learning, IoT, computer vision, so all the cool stuff that is going on, and we are coming up with different types of challenging applications so that we ourselves, myself with this channel, and we all can grow together, and we can understand the skills. And of course there's a lot of going on, a lot of things that are coming up. There's a big community of AI machine learning going on, and people are coming up with different projects, and every day some or the other new papers are coming out, so it's difficult to keep track of what it is. And I think this channel, these videos, these tutorials are going to be a good medium for us to keep up to date and also learn new things all at the same time. So if it's something that is interesting to you, if it's something that you want to join along in our journey, do hop along, subscribe to the channel, give a like so that it can help in growing this channel. And with that, I come to the conclusion. Take care, stay safe, bye bye.